So we're dealing with the normalized version of the advection-diffusion equations, for which we have the weak formulation on the top here. And in the previous last two videos, we talked about the boundedness of the linear form, so the right-hand side, and the coercivity of the bilinear form, so the left-hand side. So the conclusions that we drew so far were that if we define this left-hand side to be this bilinear form B, then we have that B, if we substitute now the same function in both slots, so W and W, then that's going to be larger than or equal to this expression multiplied by the norm of whatever function we have put in there squared, measured in H1 norm. And that made this our coercivity constant, CC. And also for the boundedness of the right-hand side, which we call L of W, we saw that was bound from above, so this is smaller than or equal to this expression, this norm of our normalized function f, multiplied by the norm of W. And again, both these expressions, right, the coercivity and the boundedness, they hold true for all possible choices W in the space H1, H10 specifically, right? That's what we're talking about here. We're talking about for all functions W in H10. All functions in H1, all functions in H1 that are also 0 on the boundary. Okay, in this video we're going to kind of talk about the last part of the story here, and that was the boundedness of the bilinear form. So we're looking for an expression such that if we substitute actually two different functions, so phi and W, that we want to be able to say, well, this is going to be bound from above by some boundedness coefficient, CB, multiplied by the norm of phi and the norm of W. And both of those measured in the H1 norm. Okay, so the main trick that we'll use here is the Cauchy-Schwarz inequality, which we've used before. And by using that inequality, we can change an inner product, an L2 inner product, into a multiplication of L2 norms. And if we look at these integrals, then really all they are is a set of L2 inner products, right? So we can actually write the bilinear form as a dot gradient phi W in the L2 inner product. That's the exact same thing as this first integral, right? That was the definition of the L2 inner product, plus the L2 inner product of, and I'll already pull out this expression kappa divided by the maximum norm of our velocity vector, multiplied by now the L2 inner product of gradient of phi and the gradient of W. And by using the Cauchy-Schwarz inequality, we can now say that this is going to be smaller than or equal to the L2 norm of the first slot here, multiplied by the L2 norm of what's in the second slot. And the same thing holds for the second inner product. Oh, it's supposed to be a gradient there. And both of these also in L2 inner products, or L2 norms. Now, one of the things we can say is, this is actually our normalized advection, right? Did I have that in mind? Yeah. So we have a normalized advection vector. What we did was we divided our advection vector by its maximum value, which means that at every point, the magnitude of the normalized advection vector is smaller than 1, which means that this is going to be bound from above simply by the L2 norm of the gradient of phi, because we're dotting it with a vector that is smaller, has a magnitude smaller than 1. And this is just going to remain to be the same. Then the second thing that we can do, and this is also a trick that we already worked with for the boundedness of the linear form is that we're going to say, well, these are norms measured in L2. But we know if we measure the norm in L2 of any function, that's going to be smaller than if we measure the norm in H1 of that same function, simply because the norm in H1 is the sum of two different components, which means that this is also bound from above by simply the norm of... Now let me be a little bit careful just to make sure that I'm not making a mistake. So first of all, I'm gonna collect this one and this one, and then we get so we get the gradient of phi in L2 and multiplied by 1 plus, no, excuse me, so it's going to be multiplied by the norm of W in L2. Yeah, no, sorry, I was saying it correct, so let me illustrate it in just a second. Okay, so but first we have this kappa divided by the maximum magnitude of A times the norm of the gradient of W. I was confusing myself for a second here. So let me restate what the H1 norm was. So the H1 norm of any function square is going to be equal to the square of the L2 norm of that function plus the square of the L2 norm of the gradient of that function. Which means that both the L2 norm of the function and the gradient of the L2 norm of the gradient of the function are going to be smaller than the H1 norm of that function naturally. Right? Because these are all positive quantities. So I guess just to state out completely what I'm saying here, that means that both the L2 norm of the gradient of phi square is going to be smaller than or equal to the H1 norm square. Now, we can simply take the square root of both sides here and we get that expression, or alternatively we can do the same thing for phi itself. And again, this would be squares on both sides and then we square root both sides. And just to be clear where this comes from, we move one of these two expressions to the left hand side, and since that's going to be a positive contribution, if we then take that to be 0, then we have an inequality. Okay, so continuing on here, what I'm going to do is I'm going to say the bilinear form of phi and W is bound from above by, and now I'm going to replace all these L2 inner products simply by the H1 norms, sorry, all the L2 norms by the H1 norms, because that's a bound from above, and then we get this is going to be 1 plus kappa divided by maximum magnitude of our velocity vector times the H1 norm of phi times the H1 norm of W. Okay, good. Which makes this now an expression for our boundedness coefficient, CB. So this is just another example of a proof for which we use all these inequalities and we come up with a bound, in this case from above, of our bilinear form, and that makes this our boundedness requirement. So what exactly did we need this boundedness for? Well, we used this boundedness in one of our analyses before, and that was for basic error analysis. And the expression that we came up with is that if we're talking about the convergence of a finite element scheme, we say that the natural norm of the error, so the natural norm of phi minus the true solution phi minus some finite element approximation thereof, measured in a natural sense, so H1, was going to be smaller than or equal to the boundedness coefficient divided by the coercivity coefficient of the bilinear form and multiplied by some interpolation constant. That's something that we got from interpolation theory, something that we really can't change. It's a fixed constant. Multiplied by h, and h was now a measure for our mesh size. So if we look back into what CB and CC are, then what we get here is that our error measured in the h1 sense is bound from above by 1 plus that expression, this relation between advection and diffusion, divided by, what was our coercivity constant? Well, that was this one over here. So that is kappa divided by CP square over 1 plus CP square. Let me check that. Yep. So what is that expression going to look like? Let's have a look into what that says. I'm going to multiply above and below the fraction here by 1 plus CP squared to get 1 plus divided by okay, let's just work this out all the way. Then we get 1 plus kappa divided by A max plus CP square plus kappa divided by A max times CP square divided by kappa CP square. So that's going to give us minus 2 plus CP minus 2 plus plus 1. Okay? And if I'm not mistaken, we can rewrite this as 1 plus CP to the power of minus 2 times 1 plus this ratio between our advection and our diffusion. Right, so now our claim on the convergence of a finite element method is that if we measure the error, being phi minus our phi h, our numerical approximation, in the h1 norm, then that's going to be bound from above by this factor of 1 plus CP minus 2, 1 plus ratio between advection and diffusion, times some interpolation constant, and h, our mesh size. So once we start to reduce our mesh size, h, well, all the other expressions are independent of our mesh. That's kind of the objective that we always have with the analysis of convergence. We want to get some constant expression that is independent on the exact choice of mesh and multiplied by our mesh size, h. So then if we reduce our mesh size, then we can anticipate that that constant remains constant, and our mesh size reduces by the fraction that we are iteratively reducing our mesh size with. So if we then draw what we expect our convergence to look like, or our error convergence to look like, then what we typically do is we take the log of both sides. So we take the log of our error, and we take the log of our mesh size, h, and then these are going to be straight lines. That's the convergence. If we start to refine, then we expect to see a straight line here. And the slope of this line is going to be the order of our method, our convergence order. And because we're measuring our error now in the H1 sense, this is going to be an order of 1. So if I decrease my mesh size by a factor of 10, then my error is expected to also decrease by a factor of 10. If I were to measure my error in the L2, we typically expect p plus 1, right? So, and I'm saying right now 1, so this is already assuming linear elements. So if I were to take quadratic basis functions, then I would get h squared, and then I would see if I refine my mesh by a factor of 10, then I expect to get a higher ratio of decrease of my error. So then I get a slope of 2, actually. But right now I'm using linear elements, which means that my error in H1 should be first order with respect to the mesh size, and we get a line with a slope of 1. Okay, and that slope of 1 is really not something that we can change unless we change the order of our basis functions, right? So if we change from linear elements to quadratic elements or something like that. So what we can look at though is that constant. So what is that constant gonna have to do with, or how is this constant going to influence our convergence graph in this log-log plot? Well, this constant is, if we plot a constant, or if we multiply a function by a constant and we plot it in log-log, then that multiplication by a constant is only going to shift this curve up and down. Yeah, so this change in constant is going to cause this curve to shift in the y direction. I'll extend this a little bit. Oh no, let me not extend this a little bit. Let me stick with this, which means that if this constant becomes larger, in the sense that the advection dominates more, then we expect this curve to go up. And if this constant becomes smaller, then we expect this curve to go down. So, and these are the bounds, right? This is we're saying the error is always going to be smaller than this expression. Yeah. So in practice, what our error might look like might be something like this. We might have something like that. Yeah. Or similarly, something like this, or something like that. And this is what we then call the asymptotic range. This is called the asymptotic range. This is where the error that we're making with our numerical scheme is approaching that asymptotic limit of first order in this case. Yeah, and everything before then, and what I mean by that is that now the green lines that I'm drawing here, they run parallel or they neighbor the white lines, and those are our bounds. So everything before then is the pre-asymptotic range. So that is where our error is not dominated by an interpolation error, but rather by a problem with our numerical scheme. So that in this case we have an unstable finite element method, and that the error that we introduce due to the instabilities in our finite element approximation are much larger than the errors introduced by the fact that we're using a finite basis, which has to do with the limit of how well we can interpolate any solution in our finite element measure. So if we now draw a certain line and call this the 100% error line, so that means the relative error is going to be of the order 1. Let me say that is going to be what I call the 100% error line. Then we see that everything that is kind of around this line or above this line would be completely useless, right? If we have a numerical simulation with an error of the order of 100%, then we have absolutely no use for this solution. So the approaches that we could do well, we could refine, right? And once we refine, so suppose that this is our numerical scheme or numerical method, Once we refine at some point, we get below that 100% error line. At some point, we refine further and further until we get to an error threshold where we're happy with. Now, that is going to be quite expensive. And it seems like that's really all the best we can do. Unless we realize that this constant also is going to be very important for us. This constant is going to shift our curve down. So by somehow, if I change my numerical scheme, improve the stability characteristics or in whatever sense, then I can push my error down already in this 100% range and get a line that looks more like the lower green line. Which means that for the same level of coarseness of my grid, I might have an error that is more of the order of 5%. Right? So this we have a 100% error here. We might have an error that's much more in the range of 1, 2, 3, 4, 5% for the same grid if we manage to push that error constant down. So let me, and we'll actually in the future videos see what kind of strategies we can make use of to try and reduce that error constant. For now, though, I kind of still want to show you with some numerical experiments that this is not fictitious. This is something that we actually see. So for now, what we saw is that this error constant goes up with our advection domination, right? So the term here is the one term that involves our physical parameters, our advection and our diffusion. And if we have a large advection domination, then this error constant is going to be large, and we would have a curve that looks like the one on the top. Whereas if this is a moderate value, we might get to one in the center. And if our diffusion is actually dominating, then we would get something like the lower graph. Yeah? So that kind of depends on the physics much more than on our numerical approximation, right? So let me illustrate you that with some examples here. And this is the graph that I showed you previous time. I think this is also something that I showed in my introduction, right? Just to rehearse a little bit. This is an advection-diffusion equation in 2D on a square with a circular hole, with some boundary conditions around the edges of the square and around the circle. And I'm plotting here the solution for different ratios of advection and diffusion. Yeah, so that's the fraction that we have right over here. And if I now plot solutions on the same mesh, then we see that for relatively moderate diffusions, I can get a pretty decent solution. And if I start to decrease my diffusion, so that ratio between the advection and diffusion tends more towards advective dominance, then we see that we start to get problems already just by representing this solution in our mesh. And at some point, well, this is a completely unstable solution, right? And this doesn't really have to do much with the interpolation. I would be able to obtain a much better interpolation of the true solution than what this is showing. So somehow the finite element method itself messes up, right? This is not the best solution that I would be able to obtain. I think we can go even further than that, and then you just get a completely garbage solution. So in terms of the convergence, let's see what these different graphs look like. So what I have here is a bunch of different curves, again plotted in the log. So this is a measure of the mesh size h in log, and this is in this case I'm plotting the L2 error here, but the same analysis holds. And this is the graph that I kind of drew here on the bottom. This is what we're seeing. Yeah, so I'm having for different ratios between advection and diffusion, I get different convergence curves. And we see that once we get to this where the advection dominates, or with advection domination, the curve is shifted upwards. Oh yeah, that was somehow the issue with my PowerPoint. Eh? Yeah. So or if I decrease my diffusion, then these curves are shifted upwards, and they're shifted into that 100% error range where my solution is completely useless. And that is something that we see that we struggle with quite a bit for these fluid mechanics problems in the finite element method. Also for coarse meshes, or specifically for coarse meshes, we just get solutions that are completely garbage. And we don't have to. If we would completely remove the advection and we'd get a pure diffusion, and you see that this is a very nice straight line, optimal convergence, very low error. This is pretty much exclusively dominated by the interpolation error, and this difference between this line and this line, to a very large extent, is based on the fact that the finite element method struggles with taking into account this advective term, right? And that's kind of what we're seeing from this analysis. But we then have this ratio here that kind of messes up our convergence. And our objectives are partly going to, okay, so the first thing that we want is for any method, we want to make sure that they satisfy, that in the asymptotic range, they have the optimal convergence rates. So that is this relation with H. For linear elements in H1, my optimal convergence rates is simply multiplication by H. And in general, for H1, optimal convergence will be H to the power P. And if we measure our error in L2, it will be H to the power P plus 1. So that's what we expect and want from any numerical method. That if we reach the asymptotic range, right, the range where my error follows that optimal path, then we want to see this optimal rate of H to the power P or H to the power P plus 1. Now we have another requirement though, and that is that before we reach that asymptotic range, we also want to have solutions that may be useful. And the issue here is that for the equations that we're dealing with for fluid mechanics, we typically never really reach this asymptotic range. If we talk about true turbulent simulations, so Navier-Stokes, a large scale, then we never get to the point where the interpolation is the dominant error in our method. It is the simulation method itself. So we're never really in the asymptotic range. We're always in the pre-asymptotic range. So what we typically want, or what we're typically dealing with, is that in that pre-asymptotic range we also have solutions that are useful. So that's what we're going to focus our attention on in the next few videos, to kind of develop fixes for the problems that we have observed here. In this particular case, that this ratio between advection and diffusion shifts our convergence curve up and down. And our general objective is always going to be to get good solutions in the pre-asymptotic range. And the first thing that we'll do is actually talk about a concept called artificial diffusion, and that's what I'll show you in the next video. Thank you for your attention.